Institute of Space Science and Technology in 2012 with a bachelor's degree in physical sciences and a specialization in astronomy and astrophysics. He then worked at Indian Space Research Organization for 3 years before leaving to pursue his PhD in physics at the University of Delaware. He received his PhD in 2021 under the guidance of Dr. Bennett Maruka. He is currently working as a postdoc at the Center for Space Physics in Boston University. His research area focuses on space plasmas, where he has published multiple papers on the interplay between microkinetics, processes, and turbulence. He is involved in a number of experimental science projects and is also committed to supporting the community as an active contributor to open source Python libraries, such as Plasma Pi. Today, Ramiz will talk about a comparative study of reconnection X-line predictions on dayside magnetopause of the Earth. I would like to remind you that this presentation is recorded, so please keep your mics muted. If you have any questions, please send them as a text to myself or in the chat box. Ramiz, thank you for accepting our invitation. Please go ahead when you're ready.
Thank you, Humayun, for the introduction. Good afternoon, everyone. I'm Ramiz Qudsi, as was just mentioned, and I'm working as postdoctoral fellow at Boston University with Dr. Brian Walsh. Jeff Brawl is another of our contributor who has contributed significantly to this project. So today I'll be talking about a comparative study of reconnection X-line predictions on dayside magnetopause of Earth. And I'll talk about a lot of these words which are in the title itself. So we will start with talking about some basics of reconnection, followed by a short discussion of a few different models which predicts the X-line locations. And then I will discuss shortly the data that I'm using for this project. There are both in situ spacecraft observation data as well as some model data. And then I'll show some results and we'll do a bit of discussion in the last few minutes based on those results. So the basic stuff, and I'm sure a lot of you have seen this or some version of this video in different presentations on reconnection. So the blue lines are the, here you have the Earth, and the blue lines are the magnetic field of the Earth, and the orange outflow, which is coming from right, is the solar wind, which carries with it both the particles as well as the field. And as it comes in and slams into the Earth's magnetosphere or Earth's magnetic field, the magnetic topology gets rearranged and magnetic energy is converted to kinetic energy and thermal energy. And there's a lot of particle acceleration which happens. And this whole process is called magnetic reconnection. And it doesn't just happen on this side, the side which faces the sun, and we generally call it the day side. So it doesn't just happen on this side, but also at the back side. But my focus is on the side which faces the sun. So that's what I'll mostly be talking about. So now this is just a zoomed in view of the same process. You have the field from Earth, and then there's the solar wind. It comes in, it interacts. There's an inflow of particle. So the next image shows it slightly better. So you have the influx of particles from both sides. A reconnection happens here, and then there's a change in topology of the magnetic field, and you have the exhaust. And then you have the jets coming out of this region because of the acceleration. And oftentimes, pretty much always, these jets have much higher velocity compared to the inflow. So, and this also leads to diffusion of magnetic flux and current concentration in the neutral point, which is this point. And in a 3D, that is a line, which we refer to the X lines. And that, if you have the location of X line, you have the location of the place where magnetic reconnection is happening, because the whole reconnection happens along the X line. And there are several models which gives you location of these X lines. I'll be talking about these four models. We have the maximum magnetic shear model, which was given by Trackner. Then you have the reconnection energy field model, the local bisection field, and the maximum exhaust speed. All these models, they maximize one or the other parameter, to find out what is the location of the X line. Now, the magnetic shear maximizes the shear between the magnetosheath magnetic field and the magnetospheric magnetic field. So you just find out the angle between the two fields, plot it, see where it is maximum along the magnetopause, and we say that that's the location of the reconnection event. As I mentioned, SH refers to the magnetosheath, MSP is the magnetospheric part. Then you have the reconnection field energy, which is the magnetic energy and it's proportional to the magnetic energy stored in sheath. And product of magnetic energy is stored in sheath and in the magnetosphere. So you maximize this parameter along your magnetosphere or magnetopause. Then you have the local bisection field in which you are maximizing the reconnection field. So what you do is you take the magnetospheric field, dot product it with the, I believe this is the direction perpendicular to the reconnection line, and you maximize that, and that gives you a location for the X line. And the fourth one is the exhaust speed, where you have a hybrid alphane. You have the hybrid alphane velocity, which depends on both the sheath and magnetospheric field, as well as the density on the two sides of where the reconnection is happening. And this is also in our case, this is the only model which takes both the magnetic field as well as the particle density. So now that we have the data, now that we have the models, let's talk about the data that I'm using for this project. Now, as I mentioned, there's both the in situ data as well as data from some of the models. We get the solar wind data from Omni, which is propagated to the magnetopause. Then we get the draped magnetic field, which is the magnetosheath magnetic field using cooling model, which in itself was derived from the Kobel and Flukiger 94 model. Then for the magnetospheric field, both the magnetospheric field is a combination of the internal, which is the purely geomagnetic model, which we get from geomagnetic field, which we get from the IGRF model, and the external field, which we get from Second Inco 96 or 2005. There's also 2001 model. Either of those are fine. There's very little difference between the two. And then from MMS, we get the actual observation at the point of reconnection. And for the particle data we get from FPI, the magnetic fields we get from FGM, and we use SPI-SPDAS extensively for getting both the Omni data as well as magnetosheath data while we are coding it. Also, for pretty much entire study, we exclusively use the GSM coordinate. The way it is oriented, you have the Earth, and the X direction is the line connecting from center to the direction towards the sun. The Z direction is towards the North Pole, and Y completes the third axis. In this case, it is pointing into the plane, and it usually points in the dawn side of the Earth. So this figure shows an MMS observation where you have the magnetosheath and you have magnetosphere, and then there's the magnetopause in between. And we see a jet reversal, which is an indication of reconnection happening. So what we do is we take such events where we see jet reversal because that implies that the reconnection was happening right where MMS was. And if you plot the trajectory of MMS along this whole magnetosheath and magnetosphere, you'll see that it goes from below the X point changes the direction so that the direction of the velocity is reversed, and then it goes into the magnetosphere. So a jet reversal is a very strong indication of the fact that there's a reconnection which happens. So what we do is we take all these events where jet reversal is there under the assumption that it satisfies the Wheeler condition, and then we try to run all our models, the 4 models which I mentioned before, and see the location of the of X line which those 4 models predict, and compare it with how far it is from the position of MMS. So let's look at some of these results. This is what a general figure will look like. You have the Y and Z plane. And it's not exactly a plane because this is plotted along the magnetopause. So, and the standoff position of magnetopause is slightly different from subsolar point, which is the central point, to a point which is outside in the limbs of this graph. So it's not exactly a plane, but it's kind of 2D projection of magnetopause. Then this gray colored circle is represents the terminator, and you have the MMS here. This shows the spacecraft which was used to get the magnetic field data. The red line shows the direction of magnetosheath field at the position of MMS. And what else? Oh, and I mentioned the model which we are using, the dipole tilt of the Earth, and the clock angle which IMF makes with the Earth's magnetic field. This cyan line is the predicted X line location for this specific configuration. And the first thing I should have mentioned is we are plotting shear. Completely forgot. So each of our plot will have one of these parameters which we discussed: the shear, bisection field, reconnection energy, or exhaust velocity. So that's what I'm showing here. And this X line is predicted along the location where the shear angle is maximized. So this is what our figure will look like. And then we find the distance of MMS from the X line along this magnetic field. So when you do that for all these different models, you have something like this, where you have the shear, the reconnection energy, it's normalized reconnection energy. Then we have the hybrid alpha n velocity, or the exhaust velocity, and the bisection field. And as we maximize them, we try to find the location of X line for all these cases. And as expected, all these models give very different location of X line. And we use our algorithm to try to find out the closest distance along the sheath magnetic field towards this line. And we see that, at least for this case, maximum shear model is doing the best job. It tells you that MMS is only at a distance of 0.66 Earth radii. That's the distance which the model has computed. Something like reconnection energy does not seem to be doing a great job comparatively. It tells you almost that the prediction of X line is almost 5 Earth radii far off from the actual observation. However, if you look at a different, if you look at a slightly different time, this is from 22nd January 2017. That's the IMF field. You see that now the reconnection energy seems to be doing the best job, whereas actually shear model seems to be doing the worst job. So it depends, of course, it depends a lot on what kind of conditions there are present. It depends on the IMF field, it depends on the density, it depends on the dipole tilt and the clock angle and all those. And the idea is to use all of this to go through a lot of such reconnection events and find out what kind of parameters are affecting the prediction of this X line, and under what condition do this model tend to do best. Because under different conditions, different models will do differently. Also, for all these studies, I've been using MMS3, but as we can see, this is from MMS3 and this is from MMS1. There is no distinction as far as the prediction of distance to X line is concerned. For all these four cases, at least up to second decimal place, they all predict exactly same distance to the X line. So it doesn't really matter which one of these spacecraft we use for this. So yeah, as I mentioned, the idea is to have a lot of such measurements, like at least a few hundred, so that we can do a decent statistical comparison of the whole thing. And so far, I have only done it for around 32 or so events, so we don't have great statistics on it. But with what we have, this is what the histogram looks like. So you have the count and you have the distance from the MMS spacecraft as between the predicted X line and the location of spacecraft. And of course, because of the low number of this, you can't really draw any conclusion. It's very difficult to draw any conclusion from this. Sometimes shear model tends to do really well, whereas at other times the bisection model or the exhaust velocity or even the reconnection energy does better than the others. So we need to do slightly more involved study of this with a lot more observations of reconnection events. So I'm working on that. However, there's one interesting thing, and the thing which we have observed is for positive BZ, the positive Z component of IMF, we pretty much all the models kind of fails, if I may say so. They all predict the location which is well outside the terminator. So of course we don't trust those observations, except for the bisection model. So bisection model still seems to be doing pretty decent job. It's not great, and this is again based on very limited observations. In fact, I think I have like 2 or 3 such observations. So this is an observation at another point where you have very low BY and a positive BZ. Again, the shear model and reconnection predicts X line way outside the terminator, which we don't really believe in. Whereas the bisection field, again, does a pretty good job of predicting the distance, predicting the X line, which actually is pretty close to the reconnection region. So discussion and understand any discussion that we are going to have is under the it comes with a caveat that we so far we haven't had enough number of reconnection events to have a significant or statistically significant conclusion which we can make. But yeah. So as expected, we do have different models do predict different location of X line for the same data set. And most models fail when the Z component of magnetic field is positive. However, this is not always the case, though. There are cases, depending on the Y component of magnetic field, there are cases when even though the Z component of magnetic field is positive, some other model like magnetic maximum shear model or reconnection energy model does a pretty decent job of predicting the quote unquote correct X line location, right?
You have 2 minutes. Sorry.
Yeah. Okay, thank you. Sorry, that broke my chain of thought. We also saw that the spread in the histogram of shear model appeared to be maximum. It's also not as concentrated as some of the other ones, especially like the bisection model. We still have to look exactly what's happening, and I think as we increase the number of observation, I'm sure histograms will change significantly. That was basically the last point, that we need a lot more reconnection events for better understanding of this whole process. But the initial results do tend to seem very promising, if I may say so. And there are a lot of other things because it does not just depend. Just drawing an X line is simple, but to see what exactly parameters they depend on and under what conditions each of these distances vary as the conditions of IMF or in changes is a bit more complicated. So I'm still working on those things. And yeah, so that was my presentation. I will take the questions if you have any. Thank you.
Thank you very much, Ramiz. That was a wonderful talk. Sorry for reminding you about the time. We need to move on for the second speaker. We have a number of questions. We see how we go along with this. If there are any questions left that I haven't asked, we will come back at the end of the presentation and then we will ask them again. But I will start with the first question here from Krishna Chandra. Wants to know which model out of the 4 gives better estimation of X line.
That was the as I mentioned, that's the whole project, right? To find out. Also, the answer is not very simple. You can't just point out to a model and say that, oh, model X, well, that was a poor choice, a variable, model Y gives the best prediction for X line. Because as we saw, sometimes, depending on the IMF conditions, some models tend to do better than the other. The purpose is to find out under what condition we can use such a model which will give you the best results. And that's still a question which we still have to answer. And hopefully by the time we finish this whole project, we will have an answer to that. So that's the hope, at least. Yeah.
Okay, thank you. The next question from Ji-Wang Zhong. In the slide introducing models, you mentioned cooling model for the magnetosheet, magnetic field. Can you explain the model a little more, please?
Oh, that, where was it? Sorry, I'm trying to think of best way to explain that. It's I can refer to a paper. I think explaining the model right now will take too much time. So if you want, I can send the paper and this talks about it. So I'm sorry, but I just feel like it will take too much time for that.
Yeah, that's fine. We can do that. Please send the link if you have here in the chat, or if you send it to us later, we will update it on our website. Thank you for that. The next question: high level of turbulence is constantly observed in the magnetosheet of the Earth, creating the great problem for the applicability of the frozen-in condition and determination of reconnection line. What do you think about these problems?
That they are there, and yes, it's a huge problem, but at the same time, I think you're gonna have to start somewhere, and we take that with the understanding that they are there, and this frozen condition is violated, but it's more like so each of these models, they have some form of they take into account turbulence in one way or another. Some does it better than the other, and based on that, they give you the prediction of these field lines. And the purpose is to find out which of these model do the best job of giving you those field lines, and that's what I think this project will help answer once we reach towards the completion. That based on so I think that's what I would say about that.
Yeah, thank you very much. I think we have time for the final question from Kyle. can you apply a similar analysis to global MHD model runs where you could potentially have more observations?
Honestly, I'm not very sure about that. As in, I don't know the answer to that question. So I'm very new to the field, so I'm still kind of like learning about it. So I'm not very confident, or I don't know what the correct answer is to that. Though I think I would say this: there are 2 or 3 of these models have been applied to some of the MHD simulations, and so if a paper talks about a specific model, they tend to show that the model does a pretty good job of predicting the X-line location. So there are studies done by different people in that, but yeah, so that's what I would say.
Okay, thank you very much. Wonderful talk again. Please stay online just in case we have more questions at the end. I will come back to you, but now we need to move on to our second speaker. And it's a great pleasure to introduce Man Hua. Man got her bachelor's degree from Wuhan University in China. She also received her PhD at Wuhan University in 2021, sorry. Yeah. Her thesis focused on the combined scattering effects of inner magnetospheric waves on radiation-belt electrons. She then joined Professor Jacob Bortnick's group at UCLA as a postdoc and continued her study on the resonant wave-particle interactions in the Earth's magnetosphere, including satellite data analysis of the Whistler mode waves and particles in the radiation belt, and simulation of radiation belt electron dynamics. Man comprehensively demonstrated that the man-made VLF transmitter waves cause the bifurcation of the Earth's inner belt during quiet times, which was published in Nature Communications and Geophysical Research Letters. In addition, Man has won several academic awards, including the Outstanding Student Presentation Awards in 2019 AGU Fall Meeting. Recently, she received the International Association of Geomagnetism and Aeronomy Early Career Award in 2021. Her talk today is going to focus on the electron acceleration effect by human-made VLF transmitter waves. Man, thank you very much for joining us and accepting our invitation. Please go ahead when you're ready.
Thank you for the introduction. Let me share my screen. Can you see my screen now?
Yes, we can see it.
Okay. Just a minute. Okay, thank you for the great introduction, and thanks to the organizer for providing this great opportunity for us to share our work here. And hello everyone, I'm Man Hua. Today my talk will focus on the role of VLF transmitter waves in the radiation belt electron dynamics near Earth space, and also whether active control of radiation belt electron population is possible. So before getting started, I would like to thank all my collaborators here for their great help and support, especially to my PhD advisor, Professor Bingbing Li, and my current postdoc advisor, Professor Jacob Bortnick. So, okay, let's get started. And so here is the outline of today's talk. I will firstly begin with a brief introduction about what are the very low frequency transmitter waves and what makes them important to study. And then I will show some results of our recent study to try to answer the question that, is active control of radiation belt electron acceleration possible? And finally, I will conclude with a summary. So before jumping into the transmitter waves, let's take a look at the inner belt electron dynamics. I believe many speakers have already introduced the radiation belt, so here I only focus on the electron dynamics in the inner belt. So typically, the inner belt electron exhibit one peak radial structure. And as shown in this movie, like the outer belt, the inner belt can also manifest various acceleration and loss process. but the time scale is relatively longer compared to the outer belt. And there are two main sources for the acceleration mechanism. One is the electron transport from the outer belt, and the other one is the cosmic ray albedo neutron decay. And like outer belt, where wave-particle interactions can play a significant role in electron acceleration, such as caused by Whistler mode chorus, the wave-particle interactions in the inner belt are mainly regarded to contribute to the loss mechanism. And another loss mechanism is the Coulomb scattering. So then let's take a look at the transmitter waves. They originate from the ground-based transmitter. So here I show a map of the transmitter all over the world. They operate at a different frequency, different power, and location. They're usually used for submarine communications and navigations with frequency lies between 10 to 30 kilohertz. And I want to mention the two most powerful stations here. One is the NAA station located at North America, and another one is NWC located at Australia. And some of the wave power can leak into the magnetosphere. And here I show a typical example of the wave electric field spectrum observed by Valana probes. We can see that the transmitter waves is typically a narrowband waves, and they're usually observed in the high density region inside plasmasphere. So they are usually peak at low L shells at L below 3. And this is a statistics of the wave intensity of the transmitter waves as a function of geographic latitude and longitude in different frequency bands. So we can see that it's easy to determine the wave comes from which transmitter on the ground based on their location and frequency band. And I marked the most powerful transmitter signals in this red box and with the detailed information given here. And it's important to understand their wave amplitude distribution. The transmitter waves has been recognized to have weak wave amplitude. So this figure shows the contribution of different transmitter to the total wave power. Please note the y-axis is the square of the wave amplitude. And we can see that at higher L shell region, the NAA station and DHO38 station mainly contribute to the total wave power. And the wave power is usually below 5 picotesla. However, for the other naturally occurring plasma wave, such as plasmaspheric heats, magnetosonic waves, and lightning-generated whistlers, their wave amplitude is stronger, especially for these two. They can sometimes even reach hundreds of picotesla during storm time. But however, in the recent study from Bernard 2021, have demonstrated for the first time of the rocket exhaust-driven amplification of transmitter waves by 20 to 30 dB, which can last for more than 1 minute. And after, we will use radar for short. And in this diagram, explain how it works. So basically, in this experiment, when the rocket and the transmitter are in the same magnetic field line, the rocket injected exhaust can amplify the pre-existing VF transmitter waves. And then at high altitude, but in the same magnetic field line, the receiver on the EPOP can observe whether this amplification is successful. So this bottom figure shows the observations from EPOP, where we can see the amplified transmitter waves by a factor of 20 to 30 dB and last for more than 1 minute. And apart from the transmitter waves from the ground station, there are also spaceborne transmitter waves. For example, one of the major science questions that DSX mission tried to solve is that, is active control of radiation bound electron feasible? So here I show the overview of the payload of DSX mission. It has a VF transmitter which can emit spaceborne VF waves. And it also has a VF receiver to detect whether this transmission is successful. Besides, it also has particle detectors to decide whether the electron in the inner belt can be affected by these spaceborne transmitter waves. And this is an example from DSX team of the observation of the DSX transmission. And it is very exciting, and we look forward to more observations from DSX. So why does transmitter waves, what makes them important? Many previous studies have linked the electron precipitations with transmitter signals. For example, this early theoretical study have shown that when including the transmitter waves, the electron lifetime can be reduced significantly at this L-shell region, approximately between 1.6 to 2.4. And here is another study based on observation, which has linked the electron precipitations with the signals from NWC station. So this figure plots the precipitating electron flux as a function of energy and L-shell. And we can see that this precipitating flux structure strongly depends on L-shell and energy, which is consistent with this red star. And this red star here shows the first order cyclotron resonance energy between electrons and waves from NWC station, indicating that these transmitter waves plays an important role in driving this precipitation. And in the following year, this study reported the simultaneously observing of the transmitter waves shown in the first two panels and the enhancement of electron precipitating flux. So the VF transmitter waves contribute significantly to electron loss in the near Earth space. And this is the most recent study from Clotpier et al. 2020, which has reported the bifurcation of the inner energetic electron belt. So here, the bifurcation means that the electron flux gradually decay and form this double peak radial structure. And we can see that this bifurcation is energy dependent, with each bifurcation deep shift to lower L shell with increasing energy. And this structure can be frequently observed during quiet time. We have a statistical paper about this, and please feel free to check it out if you're interested. And also we have a nice case study to analyze what mechanism drive this bifurcation. And in our case study, we used the quasi-linear diffusion simulation to reproduce this observed bifurcation. So this first panel shows the observation, and when only including the transmitter waves in our simulation, we can reproduce the key feature of the bifurcation, which is the significant electron flux decay at L close to 2. While other naturally occurring waves cannot drive this bifurcation. And the consistency between our simulations and observations provide quantitative direct evidence of the primary role of transmitter waves in driving the bifurcation. So it looks like the mitigation of energetic electron flux is actually feasible. And the science question in the current study is that apart from electron loss, can transmitter waves accelerate accelerate radiation belt electrons? So to address this question, we adopt the field diffusion code and quasi-linear diffusion simulations to evaluate the quantitative effect of different waves in the near Earth space. So in our method, we first calculate the bounce average diffusion coefficients, and these results serve as input to numerically solve the 2D Fokker-Planck diffusion equation, and the output of which is the electron phase space density as a function of time, pitch angle, and energy. So please note that the energy drag due to Coulomb collision is also included in our simulation. And electron scattering affected by different waves, including transmitter waves, His, lightning-generated whistlers, magnetosonic waves, and pitch angle scattering by Coulomb collision are incorporated as diffusion coefficients. Therefore, it's easy to turn on or turn off one specific mechanism to see their relative contribution. And then comes to our major results of the current study. Here I shows the simulated electron flux as a function of L shell at different energy. And this is the results by only including transmitter waves. We can see that consistent with our previous study, transmitter waves play an important role in electron loss at low energy. I should mention this simulation is performed for 30 days. But at higher energy, an interesting thing that we see is the electrons at 400 keV is slightly accelerated, although this acceleration is very slow considering the time scale is 30 days, about 1 month. So this is the result by only include lightning generated Whistlers, where we can see that they mainly reduce the electron flux at a low L shell. And this is similar for the His, which play an important role in driving electron loss at higher L shell, and there is no acceleration. And this is the result by only include the Coulomb collision, where we can see the mainly reduced electron flux at low energy. So this is the result of combined scattering effect of all these mechanisms, where we didn't see the acceleration. The reason is that the acceleration time scale by transmitted waves is relatively slow comparing to the loss mechanism by lightning-generated Whistlers and His. So this acceleration effect is hidden by other loss mechanism in the combined scattering effect. And here I show the simulated electron pitch angle distribution by only including the transmitted waves. It is important to understand the evolution of pitch angle distribution because this indicates the underlying physics that affect the electron dynamics. So here I show the electron phase space density as a function of pitch angle at different energy and different L shell. We can see that transmitted waves can cause various electron pitch angle distributions, such as the top hat distribution, which has the sharp gradient at higher pitch angle, and butterfly pitch angle distribution, which has a local PSD minimum at close to 90-degree pitch angle. And this is the 90 peak distribution. And another important point that I want to mention in this figure is that the characteristic energy of electron accelerations decrease with increasing L shell. For example, at L equals 1.8, the highest energy that can be accelerated is about 2 MeV. But when it comes to L equals 2.4, only 400 keV electrons can be accelerated here. And as we introduced in the introduction, that the radar process can amplify the transmitted wave amplitude. So we would like to find the preferred wave amplitude for the transmitted waves for electron acceleration to happen in the combined scattering effect. So in this figure, I plot the simulated electron flux as a function of energy at different scattering mechanism. Note that here the simulation time is 5 days. And within 5 days, we see that for the normal transmitted waves, there is barely acceleration can be observed. And the combined scattering effect mainly reduce electron flux at hundreds of keV. But what if we amplify the transmitted wave amplitude? Here, when we amplify the transmitted wave amplitude by a factor of 3, we can see a slight acceleration here within 5 days. And in the combined scattering effect, there is the balance between electron loss and acceleration at hundreds of keV. So what if we further amplify the wave amplitude? This is an interesting result. We can see that the transmitted waves can accelerate electrons, which becomes more significant with more intense wave amplitude. And in the combined scattering effect, we can see the net acceleration over hundreds of keV. And here we want to find at which L shell and energy range is the acceleration is most efficient. So here I plot the flux ratio given by this equation, which is the flux ratio at 5 days over the initial condition in logarithm. And for your reference, the flux ratio here corresponding to the acceleration magnitude. So when the ratio is larger than 0.3, which means the electron flux are elevated by a factor of 2. We can see that by increasing the wave amplitude, the acceleration effect becomes more significant, and the combined scattering effect can have acceleration when the VLF wave is amplified by a factor of 3. And the most efficient energy range for the acceleration is about at hundreds of keV at L shell between 2.3 to 2.8 or 9. So as we mentioned in the introduction about the radar process, which can amplify the transmitted waves by about 20 to 30 dB, and Bernard's most recent results, which is currently under review, has demonstrated the feasibility to amplification to reach higher than 30 dB. So can this acceleration be observable during the radar experiment? Therefore, we calculate the time to accelerate 400 keV electron flux by a factor of 2 at L shell equals 2.4. And in this table, we listed the amplification factor, and this is the time scale. We can see that when the amplification factor reaches 50 dB, it takes less than 1 minute to accelerate 400 keV electrons. And this acceleration can be detectable during the future radar experiment and can be directly tested from the observations. So to summarize, we have shown for the first time that transmitted waves play a dual role in both electron loss at lower energies and accelerations at hundreds of keV. And this acceleration timescale is less than 1 minute with amplification factor of 50 dB. And this should be detectable during the future radar experiment and can be easily tested from the observations. And so to answer the science question that we asked in the very beginning, the active control of radiation-bound electron accelerations driven by amplified transmitted waves is actually feasible. And our results are very important to the future radar experiment. So that's all for my talk. And thank you very much for your attention. And I'm happy to take questions if there is any. Thank you.
Thank you very much, man. That was a very wonderful talk, very clear, detailed. I think a lot of people understood, and we don't actually have too many questions. So I start with the questions that we have. Actually, questions are coming in now. So start with the first question that we have here. Is the larger, more readable world map showing VLF transmitter stations on slide 4 available somewhere?
Yeah, I think this is available in someone's thesis. I think I have the reference here. Yeah, Marshall's thesis. This is his he or she's thesis. Maybe you can also Google it from Google it. Yeah.
Right. Okay. Yeah. Okay. Thank you. I think that's clear. The next question from Kyle: what in situ observations will radar use?
The in situ measurements is from the EPOP satellite. It's here, and Bernard has about 3 papers to explain this radar experiment, and hopefully another one will come out soon.
Okay, thank you. So the next question from George is: how deep a dive did you do on the experimental data? And then he points out to some publication by Imhoff et al. In JGR in the chat.
Sorry, can you repeat that question again?
Yes. So how much of the experimental, how deep did you go with the experimental data?
I think George is recommending 2 other papers that might be of interest to you. One by Imhoff et al. In 1983, and another one by Kuk and Vampola in 1985. So those papers are just in the chat if you're interested.
Okay, thank you.
Yeah, thank you. And also there's a link to the Marshall thesis as well from 2009, if anybody's interested in the chat box. And the final question is that what can be said about the MLT dependence of the electron loss effect with VLF waves transmitted at a variety of MLT values?
This is a great question. I think because the transmitter waves has wave power peak on the night side due to the less wave attenuation on the night side. But the electron loss, the time scale of electron loss due to transmitter waves is very large, approximately from 10 days to about 1 month. So I think for a longer, from the long run, we didn't see the MLT dependence of electron loss, but when we see the enhancement of the electron precipitating flux, it should be more significant on the night side than on the day side, because the wave amplitude on the day side is very weak compared to the night side.
Oh, okay. Thank you very much.
Thank you.
I think there are more links in the chat box if people are interested. Kyle just posted the link to the thesis from Marshall 2009, I think. Anything else we get, we will obviously put it on our website later on. Let's thank both speakers again. Thank you very much for the wonderful talk. Please join us next week at the same time for our usual seminars. Is there anything else, Kyle, would you like to add?
No, that's everything. Thank you, everyone, and I hope you have a wonderful week.
Yeah, thank you for joining. Have a nice week. Bye.
Bye. Thank you.